page 9 of differentiation. Let's see, number 8. A company's weekly profit in dollars in relation to the number of units sold each week, X, can be modeled by the function f of X equals blah, blah, blah. Yay, business problem. Find the maximum profit in the value of X when this occurs. Okay. Yeah, this is theoretically a calculus problem, but you know, it's pretty hard for them to force us to do calculus when we have the calculator. So I'm going to type this in to the calculator. Hold on one second. Okay, there we go. I just typed it in. Now, if I graph this, probably nothing is going to show up on the screen. So what I need to do is I need to put, my window so that it shows like big positive numbers, because it's a business problem, right? They're working with at least hundreds of dollars. So I'm going to put X equals 0 to 100, and I'm going to put Y equals 0 to 100, and then we'll see if that's even close to what it should be. I don't need negative numbers, right? Okay, kind of. Okay, so let's increase the Y value to maybe, I don't know, 1,000, 500? Let's try 500 first. 500. I could do zoom fit also, but the problem with zoom fit, it'll show negative numbers again. Okay, find the maximum profit and the value of X when this occurs. There it is right there. How do we find that? It's a maximum point, so we do second calc max. Number 4. Left bound, we're going to move the cursor slightly to the left of the peak. Stop. Enter. Then we move the cursor slightly to the right of the peak. Stop. Enter. And then the guess, we just hit enter again. Maximum 28.8. Y equals 391. Okay, so they want the X value. The X value would be 28.9. And the maximum profit would be the Y value, which is 391.11. And since this is a money value, the profit is money, I'm going to put, cents on there. So I put 2 decimal places. All right, find the maximum profit and the value of X when this occurs. Remember, X is number of units sold, so you wouldn't be wrong if instead of 28.9 you said 29, okay? All right, number 3. A vegetable garden is in the shape of a rectangle. The garden is surrounded by 100 meters of fencing. Hint for part A, start with the equation for the area of the garden and call the length L. Okay. So what is the area of a garden? So the area of a garden is area equals length times width, because it's a rectangle. Okay, it's surrounded by 100 meters of fencing. 100 meters of fencing, so that would be like around the rectangle, 100 meters. That's called perimeter, right? So if we call the length L and the width of the garden is X, find an expression for the length. Okay, so we're going to label our rectangle here. So the length is L, and then the width is called X. And so now instead of calling it W, which I called it there, I'm going to call it LX. So the length times the width is the area, right? What about, how do I use the perimeter? So the perimeter, remember, is like going around the rectangle. So if we go around the rectangle, we add up all the lengths, it would be length plus X plus length plus X, and that would be all the way around the rectangle, right? Because these two sides are also L and X. And if I add them all up, that would be the perimeter. And the perimeter is 100, right? So it'd be 100 equals, and I could combine these two and it'd be 2L, and I could combine these two and it would be plus 2X. So there's my perimeter equation. Find an expression for the length. So what they want is they want an expression for the length, which is this L here. Guess what the kind of equation this is? This is the constraint equation, right? So how do I find L by itself? I need to do a little bit of algebra and isolate L. So I'm going to subtract 2X from both sides. And I'll get 100 minus 2X equals 2L. L is almost by itself now. I'm going to divide both sides by 2, and then I'll end up with L equals 50 minus 1X. Okay, so L equals 50 minus 1x. And that is our answer to part A. Okay, show that the area of the garden is A equals x times 50 minus x. Okay, so remember that the area of the garden was Lx. Now I have an expression for L, which is 50 minus 1x. I'm going to put that in for the L here, and that would give me A equals 50 minus 1x times x. And there we go. Just like that, right? Different order, but it's okay. 3 times 4 is 4 times 3, right? Find the derivative of A. So we're going to find the derivative of A. We're going to take the derivative of this. Remember, we don't know how to take the derivative of things multiplied together, but we could distribute the x, and then we'll get an expression that we do know how to take the derivative of. Okay, I distributed the x. Now I can take the derivative of this, right? So what is the derivative of 50x? It's 50. What is the derivative of negative 1 x squared? It would be negative 1, bring down the 2, and then I would reduce the exponent of 2 to 1. Now I'm going to simplify it. 50 minus 2x with no exponent. So this is my dA dx or a dash, whichever you prefer. So I've done the derivative. Find the maximum area and the dimensions of the garden at this point. Okay, so remember, in a different class, we would say, okay, the maximum occurs when the derivative is 0. We could set the derivative equal to 0, and then we could solve for x. Okay, you could already see maybe that it's 25, but we're not going to do that. We are going to go back to the original function. It could be this, or it could be this. We're going to put it in the calculator, okay? Let's do this one, because this is the one they give us, all right? We're going to put this in the calculator, and then we're going to find what the maximum point is by graphing it. Okay, so in y equals, we are going to put this function, x times 50 minus x. Hold on a second. There we go, x times 50 minus x. Let's check what our window is. So our window goes from 0 to 100 on x and 0 to 500 on y. We'll just change the y back to 100 because that's what we had originally, and we'll see how that works. Again, these real life problems, usually the negative part of the graph doesn't matter. So, okay, too short. Okay, so let's go back to y equals 500 and see how that works. Graph. Still too short. Maybe 1,000. The beauty of technology is you can do a lot of guessing, and it works. Okay, now we're going to find this point, the maximum point. The y value would be the area, right? The y value would be the area, and the x value would be the width. Okay, so let's find it by doing second calc, maximum, and then we move the cursor to the left side of the peak. We hit enter, and then we move the cursor to the right side of the peak, and we hit enter, and then we just hit enter one more time for guess, and the maximum value is 25. Remember, we said that maybe it's 25 from looking at this. So 25 comma 625. The 25 is the dimension of the garden width, x equals 25, and the maximum area is the y value, which is 625. Okay, and they say the dimensions of the garden. The dimension has two gardens because it's a rectangle. So the width is 25. How would we find the length? The length, we could use this expression here. So the length is equal to 50 minus x. So it would be 50 minus 25. Guess what? The length is also 25. So it is a square. All right. Turns out squares are efficient shapes. That is the last problem on page 9. Just one little bonus. I'm just going to say, okay, if you have the derivative, how would you solve this with the derivative? Maybe you might do this in an IA or something like that. We would set the derivative equal to 0 because the derivative is 0 when there's a maximum or a minimum. And then I would solve it. 50 minus 2, I'm going to solve for x. I'm going to isolate the x. So I'm going to subtract 50 from both sides. Then I'm going to divide both sides by negative 2. And I get x equals positive 25. Same answer I got before, right? So the derivative allows you to do it without any graphing. Done.